Hello, everyone. Welcome to this week's AspireCTF walkthrough. This should be the second last session. So my name is CK. I'm the mentorship lead at ICRAL Innovation Hub, and I'm going to be leading the session. And the people who will be taking us through the walkthroughs are Levanto and Alan. So Levanto was one of the participants, and Alan was one of the creators of the challenges. So both of them are people with great skills in reverse engineering, and they are very well suited to give us their perspective and take us through this session. The session is recorded on YouTube, so should you miss any part, you will find it there. And all our other walkthroughs have also been recorded and are on a playlist on YouTube. So the format we follow is that we'll start with Alan. He'll take us through the first three challenges. Then after that, we'll hand over to Levanto, who will take us through the other challenges. So I think they'll also introduce themselves before they take us through their challenges. But I think we can start immediately with Alan for the first three challenges. So Alan, you're ready?
Yes, I am.
Okay, we can proceed.
Yeah, my name is Alan, and I work with ICRAL, or rather at ICRAL. I was one of the CTF reverse engineering creators. I'm going to take you through the first three challenges that we had. Let me share my screen. Just a minute. Okay. Well, the first challenge is called, let me see if I can get to the, all right, can everyone see my screen?
Yeah, you can see your terminal.
The terminal, okay. Just a minute. All right, so this is the first challenge. It's called RE starter, and the question just says obtain the flag. So we'll download this flag. Allow me to share the terminal again. Yeah, so sorry, I hadn't downloaded it here. So we'll go to the downloads folder. Sorry. We'll run strings on the binary. It's Aspire. It's the only one there. And
we can't see your terminal.
Oh, sorry. So we'll move this file to yeah, so we have the file here. Can you see my terminal?
Yes, we can.
Yeah, so we have the file there. We'll start by checking what type of file it is. Let's run file command on it. And we can see that it's an ELF64-bit executable. So it's not stripped. So we can check the strings that are in the binary. Probably it will give us some light into it. So I'll run strings on it. If we run strings on it, we get our flag here, Aspire low hanging fruit, which we can then copy to our challenges and see if we got it. So this was a simple starter binary. All that was needed was to just run strings on the file because the binary was not stripped and the flag was just there. That's why it says obtain the flag. We'll go to the second one. The second one is an array format, and basically it implies something about format strings, and if you're a C programmer, you understand how format strings work. For this one, I have downloaded it here.
We are still on the terminal.
Oh, sorry. It's quite a challenge moving from one terminal to the next screen. Yeah, so as you can see, we've solved the first one. Now we are coming to the second one, RE format. And it says the same thing, obtain the flag. So let's see what we can do with this one. We'll move back to the terminal. I hope we can see this terminal. Yeah, we have the binary here. I'll run Radare on it. We'll start with running files. Let's start with running file on each Aspire format. It's also an ELF executable, but this one is stripped. As you can see, it's stripped, and that means if we run strings on it, we probably may not get much. Yeah, we have interesting strings here. Enter your username, enter your password, try again. We have Aspire and some %s, %c, %s. Of course, those are format strings. We also do have other strings below here, spark and spark underscore frame. So if we run stress on each, stress is supposed to show you the system calls that are being made by the binary. Sorry, I haven't installed stress. Sorry, supposed to be running it like that. Yeah, so from stress is supposed to simply tell us the system calls that are being made. We can see this one runs the binary xxcve. Then below here we see our strings being called. Enter your username. It's waiting for us to enter a username. So let's say we enter any kind of username. We move to enter your password. So we see that it exists. It exited with try again here. It tells us to try again. Let's try running without anything. We'll do the same thing. says try again. So let's run it with Radare. We'll analyze all and analyze functions and seek. We see we have main here. We can seek to main and do a disassembly of main. On Radare, we can see, of course, this is a normal disassembly assembly prologue. Then we have our string being called. Enter your username and enter your password here. Of course, there is also a call to a function after the enter your password function printf, but mostly we'll be concerned with the calls. If you look at all these calls, if you follow the calls, you will realize that the function calls will tell you something. There's a call to string compare here, and immediately after that we have, before that we have this string here that is being compared with, and this string here that is also being compared with. So this binary does two checks. It checks the username and compares it with the already preloaded string, and it also checks the password and compares it with the preloaded string, or rather hard-coded string. And if it's successful, if the check is equal, if the comparison is equal, if it's jump 0, you get either a successful login or rather a successful running of the string, and which will print the flag, our flag. So let's try to run it with these strings that we have seen, the hard-coded strings here. So we saw a string that said spark underscore frame, and we saw another string that said that. Tells us to try again. Let's try running it again, but interchange the strings. And there we have our flag. I'll move on to the third one. Let me see. Our second one is done. We go to the third one. The third one, it says RE structures. It basically has something to do with data structures in programming. Those are, so that's what we have here. Aspire AR. We'll download this binary and analyze it in terminal. Go back to terminal. So we have our binary here. I'd already downloaded it. It's also an ELF 64-bit executable, dynamically linked. It's not stripped. We can do the same thing. Let's try running strings on it. Yeah, we have these strings that are of interest to us. Enter the password, checking password, successfully logged in, login fail. Let's look at it in Radare too. We'll run Radare. We analyze all and look at the functions. We do have main. Let's disassemble main. We seek to main first, and we can do a disassemble of main. Or rather, if you're looking at this, not disassembly, rather the assembly, here, from just running it, you're already getting the flag. The flag is there. And also, we also do have the password here. Password says RE is cool. We didn't run the string. Let's try running the string first of all. It says enter the password. If we give it anything, it's checking password, login failed. So it only checks one thing, the password. For this one, you could run it using either Radare or IDA. The IDA I had installed on this machine just crashed a few minutes ago, so I'll just use Radare. Actually, we had already run this here. And we have our password here. Let's try this password. One thing I realized is that if you run this on Radare, this string translates differently. It translates a space, while on IDA, it's supposed to just give you RE is cool. So RE in capital is cool, and there's an exclamation mark at the end. Add some symbols here. Let's remove those @ symbols. Just a minute. This should be a space. I think it's an underscore. Anyway,
I think it should be a space. It's a OX20. It's a space.
oh yeah, let's check that. Yep. Yeah, it is a space. So here we find our flag, Aspire arrays. It was just checking data structures in programming languages. For this case, C programming. If we had run it with IDA, I think the @ symbol would have translated to a space instead of an @ I think that is all from me. Unless there's a question.
Right. Thank you, Alan. I think for now that's okay. I think we can immediately go to Levanto for the other challenges. Then if we have any questions, we can still have them towards the end. So Levanto.
Okay, I hope you can see my screen, the right screen.
Yes, I can.
Okay, my name is Levanto. I'm a software engineer and a member at Chasing Flags CTF team. Okay, so let's begin. So the remaining 4 challenges were somehow related. So because of this, I'll make the first challenge a bit longer and then we'll flow from there. So the first challenge says obtain the smallest key, and it gives you a link to download a binary. I had already downloaded the binary. This one, AspireCTF. So the first thing you'd want to check for information about the binary. So you do a file. So a file is a command that basically gives you more information about the file that you have, the type, things like this. So when you do it on an executable, it shows you things like, okay, this is an ELF file, 32-bit, PIE executable, and it's not stripped. So when you see an executable is not stripped, it means that it has the debugging symbols. So this means that when you're trying to disassemble, you'll be able to get the function, the labels of functions, for examples, the name of, it will be easier to debug, as we'll see. So after I do this,
could you zoom in a bit?
Okay.
Yeah.
That's fine.
Slightly more.
Okay, no?
Yeah,
Again?
that's okay.
Okay.
Yeah,
okay.
That's okay now.
All right. So yeah. So other things to check out will be like dynamically linked and like PIE. This means that the addresses, the start address of this executable is not static. So this we'll see how it will affect when you try running some tools. PIE means position independent executable. Yeah. All right. So the first thing I do is I try to run the file. So wait, what? Sorry, I know why. Sorry. That's a mistake. let's just assume that didn't happen. Okay, so when we run the file, we see wrong key. We don't know much about this, why this is showing. So the next thing I do is I try to run an ltrace. So ltrace is a command that helps you debug basically, but by showing you the calls that are made to library calls like gclib or yeah, like that. So here, so when we try to run with ltrace, we see that there is no library calls, which is a bit weird because we already saw that we are being printed for wrong key. And this means that there is a call to print, right? So we expect that there should be a call to the print function, right? But I mean, the puts function in gclib. But the reason why it's not showing is because of earlier on, when we saw that this is dynamically linked and it's a PIE. So ltrace does not support dynamically linked files. So what you can do though, you can do like that, -x to force ltrace to whatever, to look for calls to certain libraries. So by me putting a star is an asterisk to like look for all libraries, you know. So when I very sorry. So when I do this, it's a bunch of stuff because now we didn't specify which type of library to show. So this is a bit of a handful to look at. So the other thing that we can use is strace. Now strace is more low level because it shows us the calls that are made to the kernel. So ltrace showed us the calls made to the library, to like gclib, for example, but this one shows us the calls made to the Linux kernel. So when you do this, it executes and then looks for calls made. So we can see like exec, ve, mmap. Most of these things are like the program is being loaded into memory, most of this stuff. So when you say open it's trying to open to link libraries that are used. Yeah. So the interesting thing we can see here is this, right? So we see that there is a call to open a file called text file, but we have an error that no file or no file is found. So we know that the first thing the program does, it checks for a file, right? It tries to open the file. So after this, what I do is that I create the file. And then I do it again, I do ltrace. So as you can see, now we are able to open the file, right? The file is found, but then we still get a wrong key. So, okay, so now we need to investigate deeper. Let's do two things. So we open GDB. GDB is a debugger, helps to debug. What you can see now is a plugin, Jeff, that I put to make it look prettier. And then also another thing we do, I open GDRA to just show different ways of tackling the problem. Okay, so maybe we start with here. All right. So the first thing I do break main, and then I run. So it will stop at main. I put a breakpoint, and then I disassemble it. I disassemble main. All right. So trying to check the disassembled code and find some clues about that will help us, right? So one thing we see is an fopen, call to fopen. Fopen, okay, so I always try to find the functions themselves when I'm doing this, to at least know like the parameters that are passed on. So like for open, there's 3 parameters, right? There is path name, there is flag, and there's mode. This is open, right? Open. Yeah. So when you see when you see pushing, okay, so before a call is made to a function, the parameters are usually either pushed to the stack or they're put in special registers. So in this case, the parameters are being pushed to the stack before the call to open. And then the result is always put in EAX, depending on the architecture. So anyway, so we have call to fopen. We know that this is where we open our file. We have a call to fread. Fread is after you open the file, you get a file descriptor, and then you do the call to read to get the actual content. So interesting things to look at are like this. Wherever there's a comparison is a good place to start. So we have two. So we have one thing that compares if a value that is in a certain, that is at this part of the stack is 16, right? So it checks if this value here is 16. And then, oh yeah, and then we also have another check here to check if it's 0. And we have another check here to check if the value that is at AL is a lower bytes of EAX, like it's what? 8 bytes or 16? Anyway, yeah. So we check to see if it's 7A. 7A in ASCII is 7A. 7A in ASCII is Z, right? So we know that there's a call to check for Z, a call to check 16. Okay, so let's go to JIDRA and then look. So JIDRA also not only disassembles, but also decompiles the code. So I modified some variables here by renaming them to make it easier for us to follow through the code. All right. So it basically disassembled the main function, and we have here. So if we try to follow through, let me put the, I hope you can see. I'm trying to make the font bigger, but it's a bit hard. Can you see the size?
Yeah, I can see the size. So hopefully anyone using a bigger screen can see it.
Okay. All right. So we were here. So there was a call to open our key.txt, and then there's a call to read. Now, if you check the description of read takes a buffer. A buffer is a pointer to where we'll put the contents of the file. One, I didn't figure out what one is, because checking through here, let's see. Because checking through here, no, not here, sorry. Because checking through here, I could only see 3 parameters, so I didn't think to check further anyway. But we have buff. Buff is the pointer to where we put the content. We have FD is a file descriptor, what we got when you open the file. And then we have a count. So count specifies how much we are going to read. So in this case, it's 16, right? So 16, and then we get back the size. So then it checks if the size is 16. So what this shows us is that first, our file should not be empty because it checks the size. So in this case, you already know that will fail. So if we go back here and then run, I put another breakpoint. Okay, sorry. And then we continue. We'll just get a wrong key because our file was empty, right? So let's just fix that and then go back. Okay, so what was it called? Key. All right. So let's put test. That's 16. So that we. All right. Let's go again. GDB. And then we break at main. we run, and then we disassemble main. All right. So now we're sure that we will. So now we're sure that we'll pass this check here. That okay. Now our file is our content is 16, right? So if it's equal, we continue going. So now it checks if the content is 0. So okay. So when you see from here, there is a loop here. And why this is the case is because when I saw this, it gave me a clue. Because JS, it checks if signed, it checks a signed flag. So you see, it compares if the value, which is our content, right? The size of our content is 16 here, right? And then here it compares if it's 0, and then it subtracts 1. So basically, this is just like check if not equals to 0. Yeah. All right. And then it loads the content that is here to here. So this, if you can remember, I don't think, yeah, this is. So this is the pointer to the buffer that will store our content. So it's this. So basically, we're taking the content, putting it in EDX, and then when you see, when you see a string, of course, will be stored as an array of characters, right? And when we load the address here, when we load this to this, what you're basically loading is the, how let's say, we're loading a pointer, right? And then when we add 1, this is how you traverse an array. This just shows array traversal. So we're basically going to index 15, right? Because we're starting from OX10 here, which was in this. OX10 is in this, so yeah. And then compares that it's Z. So basically, this is like look through the whole string and check if the character is Z. And if yes, proceed. If no, fail, right? So if we run this, if we run this, we get a wrong key. So now from what we figured out, let's fix the text file, and then we continue. So vmp. So instead of putting text, let's put 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16. All right. And then we do, okay, so at this point, there is no point of running GDB because we figured out what the program does by just reading through the assembly. So we see that the key is correct. Okay, so when we come here, let me just cut this. Okay, where is it? Yeah. So we can just put our flag. Okay, and that's how we solve the first key. So we go to key number 2. Let me close this. We go to key number 2. And then we check. So our executable is not stripped. So that's good. That will make disassembling easier and debugging also. So let's do the same thing. Let's try to run it and see. So this time we're asked for a password, right? So let me just put test. Wrong, failed. Okay. So another thing I try to do is like try to overflow and see if there's something that if there's a segmentation fault or something. That will give me a clue if there is a buffer overflow. So I put a lot of input, but it still fails. So there must be a check, right? Either a check or a truncation of the input, such that even if you put a lot, the only thing that gets in is the size that is allocated. Okay, so the next thing we do is, the next thing to do is to keep track of this strings. They will help us when we are trying to quickly analyze the disassemble. So we know that there's call to puts 1, 2, 3, 4, 5, 5 times. Okay, so let's disassemble. Back to okay, break main, we run, and then we disassemble. Okay. All right. Okay. So let's see what's interesting here. So the first thing, we remember we had call to puts, right? So we had 1, 2 before the password. So this and this gone. And then here we have a call to Malloc. So call to Malloc takes in Malloc. See. This is anyway. Call to Malloc takes in a size, and what it returns is a pointer. Return value, it returns a pointer or null, right? So when we go back here, it's we say that the parameters are either pushed to the stack or put in special registers. In this case, it seems that they're put in special registers, which would be RDI, RSI, and if there's more than that, then ESX, EDX, like that, and then the rest are pushed to stack. So here it's RDI, and RDI is putting in this value, right? Which is A. So meaning that our input is capped at A. OXA is 10, so it's capped at 10. So that's one clue that we have. And then, okay, so after Malloc, the pointer is put at this point in the stack, RBP minus 10, right? And then there's a call to get pass. So let's put a breakpoint here. Put a breakpoint before get pass, put a breakpoint. Okay, let's run. Continue. So we just stopped here. So we want to look at the parameters that are passed inside that. So as we remember, it's ECX, RDI, RSI, EDX, ECX, and so forth. So in this case, we have RDI, which holds RX, which was OX10. What was OX10? OX10 was not allocated to anything. Oh, wait. Oh, yeah. OX10 held the pointer that we got from Malloc, right? So we know that get pass gets the address to a heap chunk, which in this case will probably mean that we put our password there. And then we have RCX that holds A, right, which is the size of our input. So basically, I would guess that my get pass takes in the input, truncates it at 10, truncates it at 10 and then adds it to the heap, right? So this is not really important to help us get the flag because we established that we can't do an overflow. So there's no point of getting into the function. So let's continue. Let's put a breakpoint at here. And then see. So we put a breakpoint at obfuscate, right? And we see what is what are passed there. Did I put? Oh, okay. Sorry, I need to put in the password. So let me just do. I put A's, as you can see them. Yeah, I put 10. Anyway, they'll be truncated. I put 10 A's. All right, so we check what is passed into our obfuscate function. So RDI holds whatever is at RBP minus 10, which in this case was the pointer to our heap chunk, right? Which at this case now holds our input. So RDI is our input. So yeah, RSI holds whatever was at RCX, which in this case is a hard-coded variable called IPass. So let's save this. Let me see if I can. Just a minute. Okay. So we have RIP. And then, okay. So we're holding something called IPass, right? It's being passed into obfuscate function. And then we have our input, and then we have on EDX, we have A. So A is 10, which at this point, I think is just capping the inputs and the strings that are used. So let's get the value of RSX, of this IPass. So let's examine this. It seems like I didn't. This is weird. Okay, let me just write it. Okay, I think I wrote it wrong. Let me see. Anyway, we can just do this. So this address here will hold the pointer to whatever is at IPass. I'm trying to write this as 1, 2, 3, 4, 5, 6, 7, 8. What did I write? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 8, 0, 1, 8. Okay, it's fine. So now, whatever we find here is not IPass, but it's the pointer to IPass. So we need to do this again to get IPass. So in this case, it's C00600F. Okay, so that's our IPass. Now you can kind of verify it from down here because we know that IPass was put at, where is IPass? IPass was put in our CX, which was put in RSI. So here it is, right? So we can see the 8 bytes, the last 8 bytes, basically, this one, which extend from here all the way to here. Now, if you remember, it's little endian, so that's why they're like this. So basically, the first bytes will come from here, and then here, and then here. So just to be safe, because we saw this, whatever, the size being at OXA, so let's just put 10, right? Let's just take 10 bytes. So let me put this here, and then so we remember that this is the first. So take this, and then we take this, and then we take this. Okay, so that's our RIP. Wait, no, our IPass, sorry. Yeah, our IPass. So IPass input and length is put in obfuscate, right? So let's just leave that for now and then continue. So we have an interesting thing down here, which is compare. We have a string compare, which takes two things. Let's put a breakpoint and then analyze what is inside. Okay, so if we continue, we're at checking password. So this is the point where it's checking the password and some other string, right? So let's see. So what was in RDI was whatever was in RAX, which OX10. OX10 was our pointer to our heap chunk, right? So in this case, it's our input. Interesting. Really? No, it's not. Whatever was at 10x, actually, yeah. Okay, just a minute. Let me see. Got a bit confused. So here, whatever is in RDI is, okay. I think because we didn't check the obfuscate function, I'm assuming things. But anyway, let's just say, oh yeah. So we remember what we say that, Okay, let me not say that. Let's just check obfuscate function before we continue. So we disassemble obfuscate. All right. So our inputs RDI, RSI, EDX are put in the stack. And then we call obfuscate function. Here. Let's just go to. Okay. Sorry. I think it's much easier if we just open it on Jidra, so that we don't have to try to check. Okay. Q2. Okay. All right. To use my mouse. Okay. Let me see. Yeah, I think it froze. Anyway, let's just go back. Do this before we check obfuscate because it will take a bit of time. All right. So string comparing. So we have this weird thing that we still don't know, right? That is at RDI and RSI, which is pass. Our pass is that we take this, which is and our pass, right? We can confirm it as so this is a last, this is a fast. We take this. We take this. And then we take this. Okay. We have string compare here that is comparing some inputs that we don't know with this and checking if it's true. Okay. So now let's go to obfuscate. Okay. The reason why I didn't really want to go into this is because to remember whatever was at RCI will be a bit cumbersome. But okay. So whatever is at RDI. Is our input, our content, our IPass. And whatever is at EDX is our 10. Okay, so this we put them in the stack, and then let's see, variable, right? We have an empty variable at ESX, we extend it to make it bigger, and then we put whatever was at RDI, which was our input. We put it to our X, we add it with RDI, we're basically traversing an array, right? Because they move it to ESI, right? The byte, the 1 byte of our input. And then we again do the same. We take an empty variable, we extend it to make it bigger, we move whatever was at RSI, which is our IPass, right? put it in array X, basically traversing the array again here. And then we move the byte into ECX, right? And then we do the same thing. Empty variable extended, take whatever was at OS, whatever. Oh, at what is this? Writing RDI, and then we XOR. So what is happening here is basically we're saying XOR ESI and the ECX, that byte, and put the byte back at EDX. That are the bytes for our IPass and our input. Okay, no. Is being XOR'd. What do I do? Is being XOR'd with our IPass, right? And then we get a value. So I bet that the value of the XOR is whatever we compare here. So okay, let me see. So here is something. We have XOR'd input, which is given by IPass, XOR'd by the original input. And we expect, by doing the string compare, we expect that our XOR'd input here, XOR'd input, is the same as our pass. So we can basically say that pass is equals to IPass and our original input. So if we want to get the correct original input, we basically just rearrange the thing. So we say original input is equals to pass and IPass, right? So yeah, that's pretty much it. So now we have IPass and we have pass, and now we need to get our original input. So let's just XOR pass and IPass and hopefully get the input. So okay, so I already have a script that I wrote. Where is it? That XORs two values and then gives back the flag. So let's modify this. Let's take our IPass. Let me see if it's the same. Okay, let's take our IPass. IPass here. Okay. So IPass, and then we take our pass, which is this. This. All right. And then, so basically what this does, it XORs it, then changes it to a hex object, and then remove the OX value, and then decodes the hex object to whatever, to ASCII. So that's what we get is just a flag. So let's do Python. Okay, so that's our flag. Our flag is obfuscate. Let's put it here. Aspire obfuscate. And we have our flag. So that's key 2. Okay, so we go to key 3. So this last challenges had a similar structure. So since we kind of went deeper with the 2, this ones will be a bit simpler. Okay, key 3. So the same thing, Aspire key 3, it's not stripped. That's good. So we try running this. It's the same thing. So let's go straight to GDB. Okay, Teamworks. Okay, what is? Oh, I forgot. Sorry, I need to remove this. Okay, so AspireCTF, let's break at main. Let's run it. Let's disassemble main. All right, so so this is pretty much the same thing, and I'm expecting that what will change will be some part around the obfuscation, but you can't assume that. So looking, it's the same thing. Size 10, put in Malloc, so our input will be truncated at 10, and then gets password, right? But there's something different here after the get password. So let's do this. Let's do this. Sorry. Let's break here. Break. Is this a good place to? No. Let's break here. Let's break after we get the password, and then we continue. So our password is I put A's, and then we break. So let's see where our password is at. Okay. So our password is in the stack still, right? Not in the stack, it's in the heap. Heap chunks. Yeah, our password is in the heap. So at this chunk, as you can see in this address this, right? So let's check that out. So what happens? So whatever is at array X, which at this point is OXA, is put into, okay, it's just put into the stack, right? And we take whatever is at RBP minus 10, which is the pointer to where our input is, right? If you can remember this Malloc here, takes the pointer. Okay, so we take that, put it in array X, and then we add 3. So we remember that when we see this, we remember that we're traversing the array X. We can check that out by stepping. So we do SI. By doing SI, we're basically stepping. So that does nothing because that was what? Where are we? Oh yeah, we're here. So we're adding our X to 3. At this point where we're at A3, right? Which, as we said, is the third index, right? Okay. So when we continue, we're taking, okay, no, let's not do it this way. Let's just go through, because this will be slower. So we take the byte at that index, right? And then, where are we? Okay, we take the byte, we put it at here X, and then we plus 1. So we're basically increasing the content that is in EAX. So it's not like the pointer to the byte, it's the byte itself. We're increasing it by 1, putting it at EDX, right? So since our input was A, so instead of 61, we'll have 62 now. So that's it. And then our input, put at RX, traverse the string, replace. So this is basically a string replace. So if we jump all the way to break, continue, and then we examine the heap chunks. Yeah, we'll see now that our fourth character is B, right? So we should remember this. So whatever character was back, right? So let's take iPass because we know what happens now. So we take this. So our iPass is at 0F, which is this. And then we'll modify. So this 8923 X 8923 B2 this, and then this. Okay, so this is out. then let's get pass, right? Assuming that it's following the logic as the previous one. So now we have our iPass. Our iPass and our input are put into obfuscate, right? And we can just check to make sure that it's an XOR. So we can do disassemble of, what? No, sorry. Okay, we can do disassemble XOR in iPass with our input, right? Okay, after that, we do a string compare. So let's jump to here to get the two things. Where is it? String compare. Let's jump here. Okay, so we'll break this. Okay, break here. Continue, and then let's disassemble main to make it. Okay, so we're here. So we're comparing pass with our input, right? So let's take pass. Pass. Okay. Pass is at 8010. It's at 6004. I have it right. 8010. Yeah. Okay. And then we take this. So we go here, do the same. Take this, take this, and take this. Okay, so that's our pass and iPass. So let's do the same thing. Let's XOR pass and iPass and get the original input. Okay, so this. Oh, I forgot. Okay. I didn't copy it. Sorry. Okay. And then pass, same thing. This. Okay. So let's do the same thing. We do Python 3 XOR.py. We got obfuscate, but we need to remember that the fourth character was added by 1. So now we need to minus 1, right? So since I don't know the ASCII value of head, let's see. Hex to ASCII. Hex to ASCII of of dot. This is what? 2E. So we need to get the hex to ASCII of 2D, which is a dash. So here it will just be a dash. And then we put that, and then we put that here. Sorry. And we solved our third key. All right. So we go now to our last one, key 4. Okay. Let's remember to do this. To do this. Okay, so similar thing, not strict. Let's go straight to GDB. AspireCTF. Tmax break at main, and then run. Then we disassemble. Okay, so we get our input as usual. We take our iPass. So let's take our iPass first. Our pass is it. Okay, iPass is this. $80.23. I think this is pretty much the same. Yeah, it's the same. Okay, so we've taken our iPass. Where is this? Yeah, taken our iPass, and then let's break here. Let's obfuscate. Break. Continue. Take our password. Okay. So similar thing. Let's take our pass before we start getting into the obfuscate function. So our pass is at 8010, which is at 6004, which is this. Does not look the same. Okay, so we have our iPass, our pass. And then we go to obfuscate. But then we need, okay, yeah. Then let's go to obfuscate. Let's check what is it, obfuscate. Disassemble. This looks our 10. So what we do, the same thing. So here we're creating an empty variable. Then here we are taking our input. We're taking the first byte of the input, putting it at ESI. Here, empty variable. But then what we're doing, we're taking, what is it, RX? We are basically increasing 1, right? To our, we're adding 1 to our pointer. So instead of index 0, we're at index 1. So our ESI had index 0 and ECX has the byte of index 1. And then we put we put the value 10 at EX. CDQ IDIV. What is this about? Pretty much forgot. Okay, let's do something while we. Let's go to import file. Documents. For okay, for this, let's use this just to make it a bit faster. Okay, so if we remember what we had at our obfuscate function, right? It's taking 3 parameters, and then it's creating a variable, empty variable local C. So there's a loop that's happening. So we can easily say that param3 is our size, right? Let's just call it size. Yeah, so we're looping through OXA, and then what are we doing? So we're taking this plus this. So this is basically where, yeah, we're traversing the array. So param 1, we're XORing with param 2, but there's a modulus function here, right? So I'd say this param 1 is our input. And then param 2 is the iPass. Let me confirm that before we continue. So we did so this that happens here is modulus, basically. But I guess because it's just like this, there's some two specific registers that it works on, maybe ECX and something else. You can have a look at that. Okay, so we remember that we had what was this? Inputs, RX, and then this, and then yeah. So I think it's the input that is being done this. Let me see. Input iPass 10. 10 iPass input. Yeah, I think it's fine. Yeah, it's fine. Okay, so obfuscate, whatever it returns is basically we have modified our input. Yeah, we have modified our input to now have whatever happens in obfuscate, right? So when we go back to disassemble main, we know that whatever we get after obfuscation is our input plus something, right? So let's just, I think there's a way we don't have to reverse whatever is at obfuscate function. So we had our original input here. So we know this input, right? So in this case, we say it's 10. I mean, it's A. So this, let me just do this. P 6, 9, 10. It's 10, right? And then here we did original input, and then in the obfuscate function, we did we got obfuscated input, which was something XOR of whatever this and this, right? So we have an obfuscated input, which we can get. And then we come to string compare. So in string compare, what we are checking is if our obfuscated input, which we will get, is equals to pass, right? So to get our, okay, so let's first take our obfuscated input. Let me just remove this. And then, okay. Just a minute. Okay. So in this case here, how we get our pass? Sorry, I'm a bit confused. Okay. So let's go here. All right. So our string compare compares whatever is at pass, right? Which is an RSI, and our input, our output from obfuscate, right? So in this case, it compares it not with the original input. No. It compares it to the obfuscated input. So we can be able to get our obfuscated input. Let's get it. It's at RDI. Where is it? RDI RX RBP minus 10. So which was in the heap? Forgot. Okay, so let's examine the 10. Which is this? Let's just get this first. Okay. Okay, and then this. And then this. What did I copy something wrong? What 3A? No, it's fine. Sorry. Okay. So our pass. Okay. So we did obfuscated input is equals to our IPass, and we XORed it with the I'm getting confused. Our input. Yeah. I think I was confusing because I was assuming that the input is what was being modified here. But now I see. Okay, so we get our obfuscated input by our original input, XORing it with something that we don't know, right? Because we modified the IPass. So we can be able to get now the modified IPass by XORing obj input and our input, right? So once we get this IPass, we know that our pass is equals to our input XORed with our modified IPass, right? So the first thing we need to do, we need to get our modified IPass. And then after that, we get our pass, right? So in this case, it's basically, all right, so let's get our modified input, obj input. Okay, let's do this. So we take this. There you go. Oh my, sorry. All right. So now we need to bypass. Let me rename this just for ease. So we have our Okay, it really doesn't matter since it's just an XOR that we'll be doing. So, okay, so I take this and my input. Where's my input? This, okay, and we want to get the hex value basically. What am I doing? Okay. Okay. XOR 2. So this is our, that becomes our modified IPass. So now we have a modified IPass. So the same thing, we have a pass and we need to get the input, right? So the input will be modified IPass XORed with pass. So we have this already. And then we go to vim XOR.py. We do the same thing. IPass is equals to, oh, I didn't copy it. IPass is equals to this. Password is equals to what? To pass. To pass. Okay. And then we do Python 3 XOR.py. And we have gotten our flag. So the point here was that the obfuscate function, you didn't really need to reverse it or anything. You just needed to do a bunch of XORs to get the flag. And that's it. Thank you. Any questions?
Thank you, Levanto. I think it was a very detailed session, and hopefully if someone missed some section, they can still go back and review very specific sections. Again, we'll also share written walkthroughs for those who prefer that format. So we'll communicate on how we'll share this. But for now, anyone with a question either through our YouTube channel from the live recording or anyone on Zoom can ask the question. If you do have a question later, you can also send it to us. We have a WhatsApp group. You can use our email address and we will try and see if we can respond to it. So any immediate question? So far, I think we seem to be okay. So thank you, everyone. Thank you, Levanto. Thank you, Alan. I hope that people learned a thing or two, and hopefully they will be able to participate in future challenges that involve reverse engineering, which we do plan to have. Tune in next time for our mobile security challenges. They also had some reverse engineering challenges involved with a focus now on the ARM architecture. So something else to look out to, and you can also use some of the skills that you have used today. So I think one question here. Is it possible to get the written walkthroughs for the other sessions as well? Yes, we will share walkthroughs for all the sessions that we've had. So for all the challenges we've had under the AspireCTF, we will have written walkthroughs too. So that means you will have both the video and the written walkthroughs for both people who like the demonstration and people who like to read and try it on your own. So again, thank you everyone, and see you during the next walkthrough, hopefully next week, unless something else comes up. So good night and goodbye.